Hello there, and welcome to my talk on vacuum energy and the Casimir effect. So, the bulk of this project for me has been about the journey from classical mechanics to quantum field theory, but today we're going to focus on an application of that knowledge to the vacuum and a curiosity known as the Casimir effect. This is an experiment where two perfectly conducting parallel plates are suspended in a vacuum a tiny distance apart. From a classical perspective, we might conjecture that nothing happens, since there's ostensibly no forces acting on the plates, but quantum mechanics proves, as always, to have other ideas. Let's look at a similar version of this experiment first. These are plates hanging in a liquid on a shaker. As the shaker increases in oscillation frequency, waves on the surface of the liquid form. Observe that there aren't really any waves forming in between the plates. The larger waves carry momentum, and their collisions with the exterior surfaces their collisions with the exterior surfaces force the plates together. So this is the object that first got me interested in doing a project like this. The Sea of Dirac, as it's known, is an early model of the universe that allows for negative energy. This diagram shows the pair creation of an electron and a positron by an electric field. Quantum field theory ultimately proved to be a better model of the universe, but Paul Dirac's model was good enough to predict the existence of the anti-electron. 18 years later, Hendrik Casimir thought of the experiment involving the plates. He used quantum mechanics and the results from a paper that he wrote with Dirk Polder to surmise that the plates would attract. A few attempts to perform Casimir's experiment were made throughout the years, but they ultimately failed because it's very difficult to get perfectly conducting plates perfectly parallel in a perfect vacuum. It took almost 50 years for the first major breakthrough when Stephen Lamoreaux used a spinning pendulum to measure the torque generated by the vacuum instead, and he got a pretty good estimate. But then in 1998, Mohideen and Roy suspended a tiny golden ball on a beam and measured the displacement when a plate was held close, which is what this picture here is. The resultant force measured was around 1.6 piconewtons, a staggeringly small amount, but in good agreement with Casimir's prediction after accounting for the different setup. The repeatability of this experiment is evidence of quantum fluctuations in the electromagnetic field. Before I can explain why, however, we need a baseline understanding of what's going on. I found this quote particularly pertinent to my project, and you'll see why shortly. Helmholtz's theorem tells us that conservative forces conserve energy. And Newton tells us that force is equal to rate of change of momentum. Most of classical mechanics revolves around these two facts, but they're important because they're our primary tools in analyzing most mechanical systems. Now, if we approximate the potential energy of some particle displaced from rest with a Taylor series, then because the potential energy is constant at any small displacement, the gradient of this will give us exactly the form of a classical harmonic oscillator, as we see here. This means that regardless of the forces that may be keeping an object at rest, the motion of any small nudge will resemble that of a ball on a spring. If we zoom down to the quantum scale, then strange things start happening. Most of quantum mechanics is done by analyzing the energy of a system using Schrödinger's equation and an object called the Hamiltonian. Classically, this is just the sum of the kinetic and potential energies. But when we transition to quantum mechanics, the momentum becomes an imaginary differential operator, and position and momentum lose their commutivity. So this is the harmonic oscillator this is the quantum mechanical harmonic oscillator. Omega is the frequency, m is the mass, x position operator, and p is the momentum operator. So once we solve this, which is a little bit more complicated than perhaps I'm making it seem here, we find that the energy is quantized. Furthermore, it's always positive. With this in mind, we can redefine our Hamiltonian to make calculations easier as we go forwards. Another important relation in quantum physics is thanks to Heisenberg. This tells us that short-lived high-energy virtual particle pairs are continuously spawning in the vacuum before mutually annihilating each other. This is the energy, this is the uncertainty in energy multiplied by the uncertainty in time is always greater than 0. This means, so each quantum fluctuation has its own frequency, and thus its own ground state energy, which will index with a continuous momentum to identify them all. This means that as we transition to the field theory, the ground state energy of the whole vacuum will be an infinite sum over infinite frequencies. This would seem to give rise to an infinite amount of energy in empty space. So how do we deal with these pesky infinities? First, let's formulate our field theory by analogy with what we just did in quantum mechanics. The properties of the vacuum mentioned thus far are founded in electromagnetic field theory, but this is a little bit too complicated to delve into here, so we're going to emulate the electromagnetic field with a scalar one. This is our Hamiltonian in this new formulation, and as mentioned, it's clearly divergent. It's actually divergent in two ways. Firstly, we have this delta function here evaluated at 0, which is an infinite volume. And secondly, we're integrating over infinite momenta. The first is easy enough to deal with. We just divide by a volume and consider energy densities instead, giving us this new ground state energy. And the second divergence is dealt with by readjusting our expectations about how valid this field theory will be at arbitrarily high momenta, giving us this new Hamiltonian. We can simplify this further by only considering one spatial dimension and one time dimension, but we still have a divergent sum. Ordinarily, we can just let the ground state energy go to 0 and forget about this divergency problem. Except, if we disturb the vacuum, then we can measure differences in the energy of the vacuum fluctuations themselves, and this is the Casimir effect. Here's our setup. We have a vacuumated conducting box and a plate in that box parallel to one of the walls. The maximum wavelength of a quantum fluctuation allowed by the width between the plate and the box is d over pi. And clearly, we see that the wavelengths allowed in the larger cavity include all of the ones in d and some more. It is this difference in energy density that it is this difference in energy density that results in the attraction between the plate and the wall. Electrodynamics tells us that the tangential components of an electromagnetic field all cancel at the surface of a metal, so we simulate this by forcing the position to be null at the plates. This bounding condition is what gave us all of those standing waves. In turn, we have a sum for the energy density instead of an integral. And we can find the force by simply taking the derivative. We're making an assumption that the frequencies are functions of d and L. Then we take the derivative and we get this quantity here. Now, if we consider an arbitrarily large box relative to the width of the cavity, then the second term, so this is our derivative. Then we consider an arbitrarily large box, and we see that the second term cancels. Now, in a project that I did with a colleague last semester, we found that this divergent sum here, this sum from 1 to infinity, this is obviously divergent, but we found last semester that this is actually the Riemann zeta function. And if we analytically continue this, then we find that, bizarrely, this sum actually converges to negative a twelfth. Now, if we apply this without too much thought, then we do get the Casimir force that we're looking for. But it's strangely convenient, and investigating the consistency of this with other forms of regularization will make up the last part of my research for this project. And so that's the Casimir effect. Thank you for listening.